Hey there, this is Adam Scripchak with STC, and we have a new tutorial for you today on adjunct properties for behavioral modeling. In SysML, we typically model behaviors using diagrams such as activity diagrams, state machine diagrams, and sequence diagrams. But did you know we can view these behaviors on a block definition diagram? Well, you can. And you can take advantage of something called the adjunct property. And it can even synchronize what you see on the BDD with a behavioral diagram like an activity diagram. First off, what is an adjunct property? An adjunct property is a stereotype applied to properties to constrain their values to the values of connectors typed by association blocks, call actions, object nodes, variables, parameters, interaction uses, and submachine states. For a behavioral diagram like an activity diagram, the call action is things like the call behavior action. And for object nodes, that could be something like the data store node or the buffer node. In this video, we'll focus mainly on the activity diagram, but in the future we can demonstrate these for the sequence and state machine diagrams as well. Let's jump into the model and create a behavioral BDD using activities for a notional coffee maker system. The first diagram we'll use is a BDD showing the domain of the problem space, and this is here to just help us contextualize the system in relation to its external entities. In this example, the domain only has a coffee consumer and a coffee maker. Next, we'll model a scenario where a consumer requests coffee from the coffee maker and provides it in response. For this, we'll use partitions to indicate who does what in this scenario. The consumer makes the request and the system provides coffee. These are all call behavior actions right now with no behaviors being called. Since the coffee maker is a system of interest, let's focus on that and turn the coffee maker's provide coffee action into an activity behavior by creating a diagram within it. We'll leave the diagram for now because we'll return to it later and update the name of the behavior. Next, I'll go to the action calling the system behavior, right-click, and create adjunct behavior. Now that we've done that, we can go ahead and create a behavioral BDD using this scenario. In the BDD, we can drag the mission scenario directly onto the workspace as an activity. And you'll see it has an attribute already populated for the adjunct property. If I drag this out, I get a directed composition relationship to the other behavior being called with the usage as a part property name and the stereotype for adjunct property. Cool, right? Let's go one step further. So let's jump inside the provide coffee behavior we created before. Again, I could right click on these, create the adjunct property, and we'll see these on the provide coffee behavior on the BDD we made before. So here, we've got the fully formed BDD with the layers of behavioral decomposition. We can even add constraints if we want to relate performance to specific behaviors, like a heating rate for the water heater behavior. One caveat, generalization doesn't work for activity behaviors like they would for blocks. When you generalize from a block, you inherit its properties and features. If you try to generalize from a behavior like an activity that has input and output parameters, these parameters won't be inherited by the block specializing it. An easy workaround is to copy and paste the behavior that you want to specialize or generalize from, renaming it and then using the generalization to indicate that this is a more specific type of behavior. This way you get the input and output parameters without having to recreate them, and you can use that behavior for, say, like a logical architecture or physical architecture white box approach. In short, it helps create a view of the behavior architecture of your system. This view can help shed light on which functions are key functions within your system, which functions are specializations of more general functions if applying a black box and white box approach, and it helps distinguish between logical and physical architectural concerns. Lastly, it enables the application of constraints on behaviors themselves, as you would with blocks, to show the refinement of performance requirements on system functions. Hopefully this video gave you some ideas on how to approach your projects moving forward. Would you like to see them used for interactions and state machines? Well, let us know in the comments below.